Alright, so last time we talked about power series. Now we're going to talk about the fact that they're actually not as bizarre as you might have thought, in the sense that you actually deal with them quite often and don't realize it. So this is 11.9. It's representations of functions as power series. Okay, so think back to section 11.2, the very first that we started talking about series. In that section, I mentioned an important theorem about geometric series that says that as long as, well, it said this. It said the sum from n equals 1 to infinity of b r to the n minus 1 is equal to b over 1 minus r if the absolute value of r is less than 1, right? Now, this same thing, well, first of all, let's consider the case that b happens to be just 1. Okay, so if b is 1, then this is just the sum from n equals 1 to infinity of r to the n minus 1, and in that case that would be 1 over 1 minus r. And by the way, this is the same thing as the sum from n equals 0 to infinity of r to the n. Okay? What this means for us is actually weird and small, but at the same time very important, because this means that as long as the absolute value of x is less than 1, the sum from n equals 0 to infinity of x to the n is literally the same thing as 1 over 1 minus x. In other words, the function 1 over 1 minus x, at least over the interval where the absolute value of x is less than 1, can be represented as this power series. Okay? Now, that seems pretty specific for right now, but let's see how this works. So, in this example, we're going to try to find a power series representation. Running out of space to write the word representation, of the function f of x equals 5 over 1 minus 4x squared, and determine its interval of convergence. Now, first of all, I just want to explain what these directions mean. So what this is asking for is it's asking us to come up with a power series that has the same values as this function over an interval. Okay? How large is that interval? Well, let's say as large as it could possibly be. And then that interval is our interval of convergence. Okay? So in other words, we're going to come up with a power series which, when it converges, will be this function. All right. So, in this case, the first thing that we want to do is we want to say, all right, well, let's see here, 5 of x, or f of x. This is 5 over 1 minus 4x squared. Now that is the same thing as 5 multiplied by 1 over 1 minus 4x squared. Okay? And so according to this theorem on geometric series, that means that that function is literally equal to 5 times the sum from n equals 0 to infinity of 4x squared raised to the nth power, as long as 4x squared's absolute value, which, you know, is just 4x squared because x squared is non-negative, but yeah, let's just leave that there for completeness. As long as that's less than 1. Okay. Well, this is the same thing as the sum from n equals 0 to infinity of 5 times 4 to the n times x to the 2n. And that's a power series, right? So this is our power series representation of the function f. The interval of convergence is wherever the absolute value of x squared is, the absolute value of 4x squared is less than 1. That's the same as saying that x squared is less than 1/4. And if x squared is less than 1/4, that's the same as saying that x is between -1/2 and +1/2. Okay? So x is greater than -1/2, less than +1/2. And so our interval of convergence is just the open interval from -1/2 up to +1/2. Okay? So what this says is just that on this interval, this equality holds. Okay? All right, let's look at another example. So this one is saying find a power series representation. So find a power series representation of f of x equals, what is this? 4 over 2x plus 3 and determine its interval of convergence. Running out of space to write the word convergence. Whatever. Okay, so for this one, we're going to do the same kind of thing. We're going to try to force this to look like 1 over 1 minus r. So this thing right here, first of all, we're going to say this is f of x equals 4. Well, 4 times 1 over 3 plus 2x. Okay. Now, if you factor a 3 out of the denominator, this becomes 4/3. 1 over 1 plus 2/3 x. One plus 2/3 x is the same thing as 1 minus negative 2/3 x. So this is 4/3. 1 over 1 minus negative 2/3 x. Okay? And so according to our theorem on geometric series, this is exactly equal to 4/3 times the sum from n equals 0 to infinity of negative 2/3 x raised to the n. Again, provided that the absolute value of 2/3 x is less than 1. This is the same thing as sum from n equals 0 to infinity of, well, I suppose we can write this like -1 to the n, and then we have 2 to the n times 4. Well, 4 is just 2 squared, so this is 2 to the n plus 2. And then we have 3 to the n times 3, so that makes 3 to the n plus 1. And then x to the n. Okay? And as for this radius, or interval of convergence, I should say, this is the same as saying absolute value of x is less than 3/2, which is the same as saying that x is between -3/2 and +3/2. So our interval of convergence is just the open interval from -3/2 to +3/2. Okay. Alright, let's see if we can do another one. So this one's going to be x over 2x squared plus 1. So, let's see here. We have x divided by 2x squared plus 1. Okay. So for this one isn't quite the same, right? But we can do the same sort of thing we did here. We can just pull out the numerator and say it's being multiplied by the fraction. So this now becomes f of x equals x times 1 over 1 plus 2x squared. 1 over 1 plus 2x squared is of course the same as 1 over 1 minus negative 2x squared. So this is the same thing as x times 1 over 1 minus negative 2x squared. By the theorem on geometric series, this is the same thing as x multiplied by the sum from n equals 0 to infinity of negative 2x squared raised to the nth power, as long as the absolute value of 2x squared is less than 1. Okay, so this is the same as x times the sum from n equals 0 to infinity of negative 1 to the n times 2 to the n times x to the 2n. So now you're multiplying all of this by x, and so this x will just distribute to each term. So this just becomes the sum from n equals 0 to infinity of negative 1 to the n, 2 to the n, x to the 2n plus 1. And that's our power series representation. It's valid as long as 2x squared has an absolute value less than 1, which of course just means that x squared is less than 1/2. If x squared is less than 1/2, that means that x is between negative 1 over root 2 and 1 over root 2, in which case the interval of convergence is the open interval from negative 1 over root 2 to 1 over root 2. Okay? All right. So, small little theorem there on geometric series. When I said it in 11.2, I made it sound like it wasn't really that important just because it was so specific to just one kind of series. It actually has big implications for power series. Next, there's one more thing that we need to know. Well, I guess it's actually two more things. Theorem. Okay, let f of x equal the sum from n equals 0 to infinity of Cn times x minus a raised to the nth power be a power series. Where here Cn is some constant sequence. I didn't mean to say constant sequence. I meant to say a sequence that doesn't depend on x. So none of the terms depend on x. They're just numbers, right? And a is just some constant. Okay. And let's say it has a radius of convergence. So with radius of convergence r, and let's say r is positive. Okay. The first part of this theorem just says that the function is differentiable on the open interval from a minus r to a plus r, and its derivative, well, if you want the derivative of this function, all you have to do is just take the derivative of each term. According to the power rule, that's just the same thing as the sum from n equals 0 to infinity of n Cn x minus a to the n minus 1. Okay. And this has radius of convergence r. Okay, so same radius of convergence as the original. The other fact is that the function is integrable on the open interval from a minus r to a plus r, and that the indefinite integral of f of x, that's the sum from n equals 0 to infinity of the integral of Cn x minus a to the n dx. And according to the power rule for antiderivatives, that's the same thing as the sum from n equals 0 to infinity of Cn x minus a raised to the n plus 1 divided by n plus 1. And again, its radius of convergence is still the same as the original. So with radius of convergence r. Okay, so in other words, what this is saying is that if you want to take the derivative or integral of a power series, you can just do it by taking the derivative or integral of each term individually. Okay. Oh, and I guess one more thing here. Strictly speaking, when you take an antiderivative, there should be a plus c, right? So I actually forgot that here. There should be a plus c. Right. Now, there are other types of functions that are defined by power series. Sorry. There are other types of functions that are defined by infinite series, is what I meant to say. We won't deal with them in this class, but they do exist. This theorem does not hold for all of them. Okay? So this is specifically for power series. If it's not a power series, you might not be able to take its derivative by just taking the derivative of each term. You might not just be able to take its integral by taking the integral of each term. But for a power series, it works. So this, too, is a small theorem with big implications. So we're going to say find a power series representation. So find a power series representation. Running out of space to say the word representation. Of f of x equals 1 over, let's see here, this is x squared minus 2x plus 1. And find its radius of convergence. Alright, well, that one's a little weirder, right? It's not quite the same as what we were dealing with before. Before it was always a linear term in the denominator, or at least not always a linear term. I guess there were some examples where it was a quadratic in the denominator, but in any case it was always constant plus or minus x to some power, right? Maybe multiplied by another constant. Okay? So in any case, it's a little bit different. Let me just draw a partition here so we don't get confused. Now, I just want to point out, this is the same thing. F of x happens to be 1 over x minus 1 squared. We can get that by just factoring the denominator, right? Now, this right here, this happens to be the derivative of 1 over 1 minus x. Right? If you understand this function as 1 minus x to the negative 1, then when you take its derivative, you're going to bring down the negative 1, so you get negative 1 minus x to now negative 2. Wait, so then wouldn't that mean that there's... Oh, wait, sorry. 1 over x minus 1. No, sorry. I had it right the first time. No, sorry. Okay. What's going on here is this is the derivative of 1 minus x to the negative 1, which is negative 1 minus x to the negative 2, and then by the chain rule, we have to multiply by the derivative of 1 minus x. This happens to be negative 1, and so the negative signs cancel, and so we just get this. Okay, don't know why that was so hard for me. All right, but the important thing is that 1 over 1 minus x, we have a power series representation for that. So this is the derivative of, let's see here, as a power series, this would be the sum from n equals 0 to infinity of x to the n. As long as absolute value of x is less than 1. And then according to this theorem, we can take the derivative of each term of this individually. So this is the same as the sum from n equals 0 to infinity of n x to the n minus 1. Okay? And also according to this theorem, it's the same radius of convergence, so still a radius of convergence of 1. So radius of convergence is 1. So this gives us a power series representation for this thing. why don't we take a look at another example. Okay, so suppose we want to find a power series representation for the arctangent of x. Some of you might already see where this is going. So if we have f of x equals arctangent x, we want to find its power series and the radius of convergence for that power series. Okay. Well, we do know that the arctangent of x, how do I say this? What I'm trying to say here is the derivative of arctangent x is equal to 1 over 1 plus x squared, right? Okay. And then that's a power series, right? So this is the same as 1 over 1 minus negative x squared, which, by our theorem on geometric series, that's the same thing as sum from n equals 0 to infinity of negative x squared raised to the n, as long as x squared is less than 1. Absolute value of x squared is less than 1, not that that makes a difference. And then that's the same thing as the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n. Okay, so that's the derivative. Well, if you want the original, then you're going to want the antiderivative of this, right? Okay. So that means arctangent of x is equal to the indefinite integral of the, well, an antiderivative of the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n dx. And so according to this theorem, we can just take the antiderivative of each term individually, which means doing the power rule on each term. So then this just becomes the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 divided by 2n plus 1. And according to the theorem, it has to have the same radius of convergence. So radius of convergence is still 1 because, well, because if x squared is less than 1, then that means the absolute value of x is less than 1, and so that's meaning that the radius of convergence is 1. Okay, so radius of convergence is 1, and then this is our power series representation of the arctangent of x. Alright, why don't we do one more example like this. This one is going to be natural log of 1 plus x. Alright, well, the derivative of this thing, f prime of x, that would be 1 over 1 plus x, right? One over 1 plus x is the same as 1 over 1 minus negative x. And so, as a power series, this is just the sum from n equals 0 to infinity of negative x to the nth power, as long as the absolute value of x is less than 1. Alright, so that's the derivative. So now once again, what we really want though is this. So we're going to have to take the antiderivative of both sides, or in other words, the indefinite integral of both sides. So ln of 1 plus x, well, this is going to be the integral of the sum from n equals 0 to infinity of negative 1 to the n times x to the n dx. Power rule, so then that just becomes sum from n equals 0 to infinity of negative 1 to the n, x to the n plus 1, divided by n plus 1. Okay? Okay. So, this is true, but I'm forgetting something that's important. I'm forgetting the plus c again. So yes, strictly speaking, there should be a plus c here. And there should have been one in the last example too, but I forgot it. It turns out to be 0 in the end. You can see that by setting x equal to 0, then the arctangent of 0 is 0, so then that tells you that c is 0. The details are in my notes, if you need to look that up. I'll do it explicitly here for this one. So for this one, I'm going to set x to be 0. If x is 0, then this becomes natural log of 1, which is just 0. So 0, that's the natural log of 1. And according to this, that is the same thing as the sum from n equals 0 to infinity of negative 1 to the n times 0 raised to the n plus 1 over n plus 1 plus c. Now, 0 raised to the n plus 1 is of course 0, which means that every single one of these terms is going to be 0. So the sum is 0. So 0 equals 0 plus c, and that makes c 0. And then if c is 0, that actually means that natural log of 1 plus x is equal to this power series, sum from n equals 0 to infinity of negative 1 to the n, x to the n plus 1 divided by n plus 1, with a radius of convergence of 1. And you know, this is our power series representation. Also, in both this and the previous example, the constant of integration c turned out to be 0. That's not always the case, of course. It's certainly possible to have the constant of integration not be 0. Okay. So, there's just one more thing that we need to discuss. See, a lot of these power series, depending on what you put in for x, it could become an alternating series. And if it becomes an alternating series, then it might pass the alternating series test. If it passes the alternating series test, then you can apply the alternating series estimation theorem to approximate its values. Okay? This means that we can sometimes approximate values of weird functions using the alternating series estimation theorem. Let's see how that's done. So, in this example, I'm going to want to find an approximation of the natural log of 3/2 that is correct to 2 decimal places. Well, by the previous example, by what we've done over here, the natural log of 3/2, well, of course, that's the same thing as the natural log of 1 plus 1/2. Now, of course, 1/2 is in the interval convergence, because the interval convergence is a radius of 1 around x equals 0. And of course, 1/2 is a distance less than 0 from 0. I mean, less than 1 from 0. So that means that this power series representation is true for when x equals 1/2. So then this actually is the sum from n equals 0 to infinity of -1 to the n times 1/2 raised to the n plus 1 divided by n plus 1. This, by the way, is the same thing as the sum from n equals 0 to infinity of -1 to the n times 1 over n plus 1 times 2 to the n plus 1. Okay. This is an alternating series, and the absolute values are decreasing, and their limit is 0. So the alternating series estimation theorem applies. That means that if we want to come up with an approximation that's correct to 2 decimal places, all we need to do is make the error less than 0.01. Okay, so here's how we're going to do this. Is maybe a little bit of a review of what we did earlier in alternating series. So remember, the alternating series estimation theorem says that the error in approximating using the kth partial sum, we call that RK, its absolute value is less than or equal to BK plus 1, where the series that we're talking about is the sum from n equals 0 to infinity of -1 to the n bn, and each bn is positive. So in this case, our bn would be 1 over n plus 1 times 2 to the n plus 1. All right. So all we have to do is make this small, and then if we do that, then the error will be small, and that will be good. Specifically, we want it to be smaller than 0.01. Okay, so we need absolute value of RK to be less than 0.01, which of course is the same as 1 over 100. So all we need to do that is just look at a few terms of B. Okay, let's see here. So B0, that would be 1 over 1 times 2 to the 1, so 1/2. B1, that would be 1 over 2 times 2 to the 2, so 1/8. B2, that would be 1 over 3 times 2 to the 3, that becomes 1 over 24. B3, that would be 1 over 4 times 2 to the 4, which is the same as 1 over 2 to the 6th. 2 to the 6th is 64, so this is 1 over 64. B4 would be 1 over 5 times 2 to the 5, 2 to the 5 is 32, and then multiply that by 5, what you'll get is 160. Let me just check my notes that I did all that arithmetic correct. Yeah, looks like it. Okay, and then this is as far as we need to go, because now this is smaller than 1 over 100. Okay, so the alternating series estimation theorem says that the absolute value of the error in taking the n equals 3 partial sum, or k equals 3, whatever you want to call it, this is going to be less than or equal to B4, which we know is 1 over 160. And that, of course, is less than 1 over 100. And that's what we wanted, right? We wanted the error to be less than 1 over 100. So, this means that natural log of 3 halves is approximately equal to, let's see here, 1/2 minus 1/8 plus 1/24 minus 1/64, and that's it. And when I say approximately, in this case I'm saying correct to 2 decimal places. Okay? So that is our approximation for the natural log of 3 halves. Alright, so homework is up. Go ahead and get some practice with problems like that.